Good evening, everyone. Let's get started today. We'll start with a quick review of last week's regarding constraint optimization. We'll look at some examples and then we will also be discussing about penalty methods. And from there on, we'll take one example of the previous algorithms which we discussed on differential evaluation and how to adapt that particular algorithm to combine it with penalty function to obtain a solution for a given problem. And from there, we'll take on to some of the multi-objective optimization, basic introduction concepts of what a multi-objective optimization is, and we will see some techniques for evaluating, for solving such problems. Yeah, we'll now get started with this particular problem. Say suppose you have an objective function f of x comma y given by y minus x. This is my objective function. And these are my set of constraints. Say suppose it did not have the bounds on a variable as such. So how do we go about solving this particular problem? So if it had been the original problem of just f of xy without any constraints, we would have approached using the normal del f by del x equal to 0. Del f del x equal to 0 and del f del y equal to 0. This particular one will give us -1 and this particular one will give us 1, which essentially do not have any optima as such. This is the necessary condition which states if a stationary point has to exist for this particular function f of x comma y, then we need both of these conditions to be satisfied, which is not the case with the current problem. But when you are given the bounds as here, let us see what happens because of the constraints. Just to get a overview, we will see graphically these constraints are like x plus y less than or equal to 1. So these are essentially the constraints. So the region in between, this particular region in between, which encompasses all your boundary conditions, all your constraints, is essentially your feasible region, feasible space. So this is your feasible space. So within this feasible space, what we are trying to do is to minimize this particular function y minus x. So the value of y minus x can be anything. So let us say if y minus x equal to c1, our objective is to find this value of c1 such that all these constraints are satisfied. All these constraints are satisfied, and at the same time, we need to get the maximum value of c1. Sorry, minimum value of c1. So y minus x equal to c1 is a line which is a 45-degree line, whose intercept can vary. So essentially when we are trying to minimize, what we are essentially trying to do is move this line across a space. So when it comes to this particular, actually this should be parallel to this. So ideally this is the minimum value that y minus x can encounter on this particular line where y minus x will be minimum. Like any point above this will kind of increase the value of my y-intercept. C is your intercept, that is when x equal to 0. So this particular intercept is minimized at this particular value. So this particular intercept value is -1. So the minimum value is this particular line. So how do we go about solving this? Like the last week we discussed about a method called Lagrange multipliers, which is used for equality constraints, and then we also discussed about KKT conditions, which are usually used for these kinds of problems. So what essentially are we trying to do in this KKT? KKT conditions is this. I have my original problem f of xy that I need to minimize, subject to some constraints. Here we have let's say Gj less than or equal to 0, where j equal to, in our particular case, 1, 2, 3, 4. These are the 4 conditions. Say G1, G2, G3, G4. Note this particular thing, that all these Z's should be reformulated in this particular way. Like Gj should be less than or equal to 0. If you can see this particular constraint, here it is greater than or equal to -1, and all these are less than or equal to 1. All these constraints have to be written in the form of Gj less than or equal to 0. Only then we can substitute in our KKT conditions. So if we were to do the same, this is what we are going to do. So we'll get, let me define another function, say L of x comma y, comma, we'll have some parameters to quantify the C's of this, which we will discuss now. Say we have 4 constraints. So let's say u1, u2, u3 and u4, and we define this function like this. So we have f of x comma y plus u1 times g1 plus u2 times g2 if we formulate this particular solution, if we formulate the problem in this way, and we say what we are essentially trying to say now is minimize L. Now, as you can see, like here we essentially have like one equation, but we have instead of the original problem, we essentially have only 2 variables like x comma y. Now we are having another 4 more variables which we cannot solve directly. So we need 4 other conditions to be able to solve this problem. So how do we get those 4 conditions? So to minimize this, we can kind of state this as dou L by dou x equal to 0 and dou L by dou y equal to 0. So with this I got 2 equations. Now for the second case, how do I go about getting the other equations? Or essentially, when I am trying to minimize the value of L, I need to, and all my G values, all the inequality values are less than or equal to 0. If I get a value of G positive, then when I am trying to minimize the value of L, it should essentially decrease the value of L, which means finally when I get a solution, the solution should not have any impact on this. So my requirement is like u1 g1 should be 0, u2 g2 should be 0, u3 g3 should be 0, and u4 g4 should be 0. Only if this particular case is satisfied, then we are essentially having minimizing L is equivalent to saying minimizing f of x comma y, because all these other coefficients over here will turn out to be 0. But as you can see, now we have essentially 2 plus 4, 6 equations, and we have 6 unknowns. So if we solve all these 6 plus 6 equations and 6 unknowns, we will be able to get all the values of x comma y and u1 to u4. But there is a catch here. As you can see in this particular formulation, if you try to minimize the value of L, your value of g1, g2 to g4, if all these values are positive, if g1 to g4 are all positive and you are trying to minimize it, then you will come to a feasible region, into your feasible space. So if your g1 is positive, which essentially means you have some point over here, say you have some point in the outside space, and this particular point, our objective is to move this point towards into the feasible space. How do we go about doing that? This can happen only if while minimizing L of x should drive the point into the feasible region. So if you have, this can happen only if u1 is greater than or equal to 0, u2 is greater than or equal to 0, u3 is greater than or equal to 0, and u4 is greater than 0. Why is this? Essentially because if for suppose u1 is negative and your g1 is positive, then the entire product, if say suppose u1 is negative and your g1 is positive, the product u1 times c1 will essentially go negative. So L value will be like f minus u1 f plus u1 times c1, where this quantity is negative. So even though the actual solution g1 greater than 0 is not feasible, this is an infeasible solution. So when we are having an infeasible solution, this is kind of driving my Lagrange value, L value, to be even lesser than what it was supposed to be. So when we try to minimize this further with the same negative value of u, what it will try to do is essentially increase the value of Gj. So in this particular scenario, when I try to decrease the value of L for a given f, what it will try to do is it will try to increase the value of G1. Since U1 is negative, this will in overall tend to decrease the value of L, which is not what we expect, because we are in the feasible solution only if G1 is less than or equal to 0 first. So in order to have this particular criteria, we kind of propose an additional condition saying U1 should be greater than or equal to 0. If this particular one thing happens, then when it is greater than 0, this will be greater than 0. So this quantity over here will also be greater than 0. So this value of L will be more than what it was supposed to be. In that particular scenario, if your U1 is greater than 0 and your G1 is increasing, your L value will increase. So when you try to minimize the value of L, you will essentially, so if you want to minimize L with U1 greater than 0, you have only one option, that is you have to decrease the value of G1. So from positive value of G1, you will gradually move towards regions with negative values of G1, which is equivalent to saying decreasing the value of G1. So this collectively, all these constraints put together is what you call the KKT conditions. Let's write them one by one and solve one problem. So the first condition is del L by del X equal to 0, which gives me my f of xy is y minus x. So let me just write down the original value of L here. So my L is f of xy is y minus x plus we have u1 times g1. G1 should be written in such a way that it is less than or equal to 0. So as you can see here, g1 is x plus y is less than or equal to 1. So if I have to write this in the particular format which we required over in this particular format which says gj is less than or equal to 0, what I essentially have to do is a simple so it's x plus y minus 1. Similarly, u2 times g2 is minus x plus y minus 1 minus x plus y minus 1 plus u3 times, and for the third condition we have minus 1 minus x minus y minus 1 plus u4 times we have the last one x minus 1 minus 1. So this is my L function. So now let us write down the equations one by one. So the first equation is del L by del X equal to 0. This gives me minus 1 plus u1 minus u2 minus u3 plus u4 equal to 0. My second equation is del L by del Y equal to 0. This kind of gives me 1 plus u1 plus u2 minus u3 minus u4 equal to 0. The next set of 4 equations are essentially from my KKT conditions, which gives me like u1 times g1 is x plus y minus 1 should be 0, and u2 times g2 is minus x plus y minus 1 equal to 0, and u3 times g3 is minus x minus y minus 1 should be equal to 0, and u4 times g4 is x minus y minus 1 equal to 0. In addition to this, we have the other conditions as we have seen are essentially u1, u2, u3 and u4. All of them should be positive values. Now these are my set of equations. When I solve all these equations simultaneously, I should be able to get the solution of x, y and the corresponding values of u1 to u4. How do I go about solving this? So let us name each one of them. So let's say 1, 2. All these equations are from 3 to 3, 4, 5, 6. And so I have all the 6 equations. So if you are about to add equations 1 and 2, you get an interesting relation which says u1 minus u3 should be 0. This implies u1 equal to u3, and if you were to subtract 1 from 2, you'll be getting another set of equation which is essentially like when you subtract 1 from 2, so your u1 goes away, so you'll be left with u2 minus u4 equal to minus 2. We can write this in another way, where which is u4 minus u2 is essentially 2. Since we know that both u4 and u2 are essentially positive, which means like u4 should be greater than or equal to u2, and this should be greater than or equal to 0. So let us start with our basic values. Say suppose if with the set of equations, say suppose we can start with say from equation 3, we have two possible conditions, either u1 equal to 0 or x plus y minus 1 equal to 0, or you can have both. Similarly, for all such equations, we'll be having this set of possible conditions, either u2 equal to 0 or the g2 equal to 0, or you can have both. Similarly, u3 or g3 equal to 0 or both, and you will be having similarly for the last one, u4 equal to 0 or g4 equal to 0 or both. Let me just write down all of them, and then we will solve each of them. u2 equal to 0, or you essentially have minus x plus y minus 1 equal to 0, or you can have both of them. So from the fifth equation, you will be having u3 equal to 0 or minus x minus y minus 1 equal to 0, or you can have both. u4 equal to 0 or x minus y minus 1 equal to 0, or both. Now let's just see the options over here. You essentially have the first constraint which says u1 equal to, the first one over here which says u1 equal to u3. So let us start with the case u1 equal to u3 equal to 0, and also we have another case which says let's say u2 is equal to 0, which means u4 will be a value of 2. If u4 is some finite value, then from the sixth equation, what we essentially have over here is, if u4 is some finite value, then our only possibility is like x minus y minus 1 should be equal to 0. This is our only case. So as you can see, with these conditions, when u1 equal to u3 equal to 0 and u2 equal to 0 and u4 equal to 2, we have satisfied 1 and 2, and since all of these are also satisfied, in order to satisfy the sixth equation, we are keeping this. So which essentially gives us y minus x equal to a value of minus 1. So this is our minimum value. This is the same value which we are getting even from a graphical and intuitive way. So you can see, like when you move this y minus x line, it can actually range from a value of, say, here y minus x value is an intercept value of x is a value of positive 1, and it gradually kind of decreases as you go. It comes to a value of 0, and then again it kind of gradually decreases till a value of minus 1. If it would not have been that because of constraints, it's only because of the constraints that we are obtaining a value of an optimal value. If there had been no constraints, then it essentially we don't have any stationary points. So I think this is clear. Now as you can see, like here it kind of got us simplified here. We can have other possibilities as well. So let us have a quick look at some other possibilities. So if you see the equations over here, essentially you want u1 and u3 to be equal, but n essentially cannot be 0. So let us consider another case. Say u1 equal to u3, but they are not equal to 0. In that particular scenario, say suppose still your u2 equal to 0 and u4 equal to 2. So with these particular constraints, what we get is when u1 and u3 are not equal to 0, this kind of boils down to saying then the other g1 has to be 0 and g2 has g3 is 0 minus x minus y minus 1 equal to 0. If you were to solve these two equations, then these are a set of parallel lines which do not have a solution as such. So you will never be able to get a solution of x comma y. Similarly, you can have other scenarios. Let's say the other case. u1 equal to u3 not equal to 0. u2 is some finite value greater than 0, which kind of gives you u4 has some positive value of 2 plus that finite value of u2. Even this solution will also kind of lead you to the same value, saying x plus y minus 1. So this also kind of leaves you in the same problem. So when you are having u1 equal to u3 not equal to 0, then you will be left with these two values, these two equations, which you will not be able to solve since they are a set of parallel lines. So you are again living with no solution. So the only solution is this particular value. As you can see again, we are only kind of obtaining the optimal value here. We do not know which particular value of x comma y will give us this optimal value. As such, say any value on this particular line. So if you happen to see this line, this entire equation, this entire line over here, this entire line, as you can see over here, is a possible set of possible solutions within the domain. So you do not have a unique solution which kind of gives you the optimal value. But you can see, like in this particular case, with just 4 constraints, we have several possibilities. As such, here you have 3 plus 3 plus 3, 3 into 4, like 12 possible ways that you have to go through each one of them. And then with these additional 2 constraints, that kind of got reduced for us with only 2 possible scenarios, and you have to go through each of these solutions. But imagine a real problem, real world scenario, where you will be having like literally like 100 constraints with you, and to be able to solve all the 100 constraints together is really tiresome. And this approach may not work. Even with and in addition to this, other complexities also will come in terms of say here we have a function which is kind of differentiable. The particular function we have chosen is a very simple function in terms like y minus x. So we were able to obtain the value of del L by del x and del L by del y, which is not the case with in real world scenarios. We'll have functions which are non-differentiable, which are not continuous. So how do you go about solving them? The general approach to solve these problems is using penalty functions, which has been discussed by the professor in the lectures. So now we will go through one example to understand how this actually works out. Give me a second. If you remember, this is the same workbook we are using previously for understanding about penalty functions. So yeah, so we'll consider the same problem which we considered previously. So our objective is to minimize the value of f of x equal to y minus x subject to the constraints in this particular way, which kind of gives you the same problem as this. But now we are trying to solve it using an evolutionary computation technique. So the technique we have chosen here, is a differential evolution. So this is the simplest to implement in terms of it doesn't have much of the parameters. It essentially has only one parameter, which is your crossover rate. So we'll see how to actually implement this. And as you can see, like there are several kinds of penalty functions. So what are we essentially trying to do? The approach here is like, if you are to deviate any constraints, you will be penalized for deviating that. And as you go on penalizing you, this will kind of motivate you to move towards a feasible space. So say suppose so if this is your feasible space that we are speaking about, this is your feasible space. What we are trying to do is whenever you find a solution or whenever you have an individual in evolutionary computation, we have the individuals. We have several individuals and we kind of gradually calculate their fitness values and see how they evolve over time. So what happens is when you have a solution which is infeasible in the sense it's outside the feasible space, then what you have to do is essentially kind of drive that towards the feasible space. How are we going to deal that is essentially by imposing fines. Say it is kind of similar to what we do in case of a traffic where you essentially have some fines put on you, which will kind of give you say suppose you violate some traffic rule, you will be given some fine. This kind of penalize you in such a way so that you will be gradually oriented towards ideal way where you have to follow all the rules. So these are kind of similar approaches, and they also have the similar kind of policies where too much of a penalty will kind of drive you in other ways, and we will see about them in detail. But for now we will see how, like, this is how we will do. So mathematically this is equivalent to saying now we will define a new function, say p of x, where this p of x now has to have three different components. So one component is actually objective function that we are trying to minimize, and then we also need to have some information about your constraints. Say usually in our original formulation, what we have is this. Let's stick to our original formulation. Minimize f of x subject to the constraints gj less than or equal to 0 and hk equal to 0 within some bounds, say x lower less than or equal to x less than or equal to x upper bounds. These are the variable bound constraints. In this original formulation, if you were to see, then we should have some information about gj, and similarly we should have some information about hk. All this has to be somehow kept in a form that this penalty function takes. So when you are trying, essentially, then what you do is essentially minimize the value of p of x, which will kind of motivate you to minimize the value of f of x and to minimize gj and to minimize hk. And this gj and hk should not be put as it is, since because if you have an inequality constraints, anything less than is fine, but for hk of x you want it exactly to be 0, so directly posing in this particular way will not be useful. So you essentially have to have some functional form. I'm just denoting it with a bracket over here, and then say with a mod over here. This is just one approach. You can use any other approaches. We will see what these functions are actually, but what I essentially intend to tell over here is, like, you should not use the actual values of the constraint violations. You will be using some functional form of the constraint violation into the penalty factor. Now, next, how do we combine all these effects into the penalty function? We use a simple linear combination of all of them. And then what we essentially do is, there are several ways to go about it. It's essentially, fundamentally, it's like you will be having your penalty function has essentially three components. One about your objective function, and then you have inequality constraint violations, and then you have equality constraint violations. So all of this information has to be somehow brought into the p of x. The first approach is to this comes with, so we have several techniques which we will discuss briefly. So as we have seen, like your penalty function p of x will essentially have a component from your objective function, and then you have some component from your inequality constraint, and then you have some other component from your equality constraints. How do we go about getting these values is what we are going to look now. So there are several ways to go about it. We will start with what is called, the first approach is essentially what is called a death penalty. How do we get death penalty? What we do here is, we have a certain set of individuals, and if any of these individuals violate the constraints, then what we do is remove that individual from the population and regenerate it. Yeah. So we remove that particular individual from the population, and again we regenerate the solution. Say suppose let us take one example. So we are having these 4 individuals. Yeah. Say if we are having 4 individuals with the following function values of say 2.0, 3.0, 4.0 and 5.0 with the following value. Say we have only one inequality constraint, and the values are something like 2.5, 3.5, minus 1.2 and minus 4.0, and you have only one equality constraint, which is more or less 0, 0, and kind of all of them are satisfying the inequality constraint. This is just a sample case. Say suppose if we have in this particular format, you have your objective function values as this, and these are your inequality and equality constraints. So what we do in death penalty is if any of the solutions are infeasible, then you remove them from the population. So if you can see here, if our original problem, our formulation is in this particular way. If you want to minimize f of x, subject to the constraint gj of x should be less than or equal to 0, and hk of x should be equal to 0. In this particular form, if you see in this particular form, so anything which is less than or equal to 0 is a feasible solution. So these two particular solutions which are positive are infeasible. So we have to eliminate these two solutions. So this solution and this solution will get eliminated, and the remaining will go to the next generation. So what we do here is again generate two other individuals. So the next time we generate individuals, we again get some another values of f of x and corresponding constraint violations, and we do it till we get a value which are feasible. So as you can see the limitation right here, like since we are generating these individuals randomly, we might end up generating so many individuals which are infeasible. Especially this happens in cases where you have more number of constraints and your problem is constraint driven, then you might encounter regions where whatever point you will be generating more or less will be infeasible. The probability of generating a point which is infeasible is much higher compared to the feasible points. So the next approach is like instead of rejecting, what we are trying to do is, and there is another problem which comes up is something like this. Say suppose you have, say suppose this is your feasible space, you might actually get some point just very close to the boundary, and maybe it can happen that in your particular case your optimal value is somewhere over here. By actually rejecting the previous point, or say suppose this is your optimal point, so when you actually rejected this particular point, you actually missed one of your opportunity to get closer to your optimal point. This can also happen. So the idea is like we should not reject that. Instead, we should use that and somehow drive that particular point towards reaching into the feasible space. That is what we do in the next approach. That is what we have called static penalty. What we essentially do in static penalties, instead of rejecting the points, we use information about them. How do we formulate? So we take our basic rule where your original penalty function is some combination of your objective function and some combination of your inequality constraint violation and some form of your equality constraint violation. So here what we do is we define two parameters. Say let it be R1 times some power of alpha and R2 times some power beta. So what we are essentially trying, and this bracket function here is can essentially take two possible values. When you are actually violating the constraint, this particular the value of that constraint violation should be added to the penalty function. So when you actually violate the constraint is when g of j is greater than or equal to 0. So only in this particular scenario, you take the value of the constraint violation when gj is greater than or equal to 0. If otherwise, you just do not take that value. In that particular case, your contribution to the penalty term should be 0. So this is how you define the bracket function. In case of equality constraints, any value which is not equal to 0 is a constraint violation. So that essentially adds up to your penalty. And this R1, R2 are your penalty parameters, and similarly alpha, beta you have to decide. Usually we take a value of around alpha, usually we take around 1, and your beta will be usually 2. If you are not having this absolute function, you have to keep 2 essentially because you need to take care on the both sides. If h of x is either positive or negative, both of them are considered to be deviations in the constraint. But as you can see, in this approach, once you fix the parameters of R1 and R2, they remain constant throughout. So usually what happens, initially generated solutions will more or less be infeasible, and as you apply this penalty over the generations, they will gradually become, so just to give you a perspective, say initial solutions are something like this, and you have some feasible solutions. What essentially happens over time is all these solutions will move into the feasible space. Once you move into the feasible space, the penalty parameters has no such role as such. But it can also happen that more of these, some points might stay just around the corner, and they might not actually come into the feasible space, but then you are actually penalizing them at any point which is very close to the boundary, or which is actually too far from the boundary. Both are getting penalized, and this penalization should be kind of somehow dependent on how your generations are actually progressing. When initially more number of solutions are infeasible, then essentially imposing more higher penalty will kind of drive them into the feasible space much faster. But as more and more points come towards the boundary, you might have to decrease the penalty parameters a little, so that you can smoothly make them transition into the feasible space. Otherwise, what could happen is these points can actually be too far. Yeah, you have some questions?
Hello, sir.
Yeah.
Yeah. How to select alpha and beta R1 and R2?
Yeah, your alpha and beta are like alpha, you usually choose one, but there is no hard and fast rule as such. You need to go only with this particular value. It's the same as like all these techniques are
Beta.
kind of heuristics. No, it's kind of a trial and error. You have to try with these values, but beta should be kind of an even power, just to ensure that h of x on it has to be taken care both negative and positive values, so it should be some even power. But alpha can be any value as such. But if you give too
And
high,
this R1 and R2?
R1 and R2 depends on the scale of your problem. Say suppose you have an objective function value f of x which ranges around say only 0 to 1. Then your R1 and R2 will also be in the same range. It's like you essentially don't want to give too much.
If I take high value of R1,
then your problem would be changed.
It may deviate.
Yeah, it will deviate. Yeah. Then your problem will change. Like now you're essentially, your problem was actually changed by this formulation. So here we are not essentially trying to minimize f of x, but we are trying to minimize p of x. And when you have two high values of R1 and R2, then f of x will be insignificant.
This is the problem with the penalty function. Selecting of R1 and R2.
Yeah. Yeah, that's you have to do with some trial and error. We cannot say beforehand like this should be the value of R1 and this should be the value of R2. And actually it should change as you progress. So we will see with other methods how this is actually done. So in this particular approach, your R1 and R2 are fixed, and that might not be ideal case. So during the starting stage where you have lot of infeasible solutions, imposing a very high penalty will kind of drive you towards feasible region. So
high means how much?
High comparative to your. It depends on the value of your G. Like your inequality constraint violations, they are like already 10,000 or 20,000. Then your R value doesn't have any impact, right? If your function values are bounded, say suppose are within 0 to 1 or something, then putting a R value of around 0.5 will be sufficient, right? Like it depends on your functions.
It depends upon, okay.
You cannot decide before ahead, but once you decide some function, then you can see how it progresses. Depending on
so
that,
automatically
you change this
we can take from the mod of GJ.
Okay, it's not essentially mod, it's some different function. Okay. Like as you said, like this static penalty is not is very rarely used. So we will discuss some other method which we use actually. We'll come to that. We'll just go with this. Like we'll just stick to the plan. Yeah. So as you can see, like there is a problem with this particular method. So what we essentially do is we do not want to keep these values of R1 and R2 as constant, and even your alpha beta. Like how do we go about changing them? One approach is what we come up in dynamic penalty. Here the idea is why do we have to fix the values of R1 and R2? So what we essentially do is we vary them, but vary them according to the time generation. So initially you will have a high values and gradually they will be kind of decreasing. Or you can pose it other way. Initially you will have low values and you can kind of increase it. So how do we put it mathematically? Is you take an objective function and then you take some constant and you take the value of t, which is your generation, times power alpha. This will decide how actually it grows with respect to your generations. Times again you have some parameters, say r1 times your gj of x. Actually there will be some, if I am actually writing in this particular way, then there should be summation of, and we essentially have the bracket function over here, gj of x times say some beta, and again you have summation of rk times hk of x power say some gamma. This summation is over inequality constraints, and this summation is over, this is our equality, and this is around the inequality constraints. So it is similar to the static penalty, but the only change we are essentially making is in this particular term. This particular term will add to the dynamic, in the sense it will kind of change over generations. So you can kind of decide the value of alpha. If you keep a value which is greater than 1 for alpha, then it will gradually increase. As your generations increase, you are kind of increasing your penalty parameters. And if you put a value of alpha which is less than 1, it kind of goes the other way. But this is also not kind of the one which we require. So what we require is essentially I have to keep in mind what the previous solutions are and then use them. If we can use them in some particular way to kind of tune the value of these parameters is what we do next. This is what we call an adaptive penalty. The idea is simple. We just take the previous case. So we just say penalty function as my objective function plus some constant times my inequality. You can actually put alpha, or you can kind of make it equal to 1, and you have some equality constraint for beta. The idea is in this parameter lambda, which we kind of change as we go through generations. How are we going to change that is essentially we have 3 particular cases. So we do not change the value of lambda always. Say suppose in your last some set of generations, you are continuously getting infeasible solutions, which means the way you are driving your algorithm is not actually helping you to move from infeasible space to the feasible space. So you essentially have to have a very high penalty factor to drive this change. So what we do, we scale the value of lambda. If say I'm just assuming beta is greater than 1. If beta is some parameter beta which is greater than 1, then I'm multiplying lambda with this particular parameter. If I do this, what am I doing is essentially increasing the penalty value. I do this only if my last, say suppose some generations, say 1, 2 or maybe some 5 and from last k generations, what I am getting are all just infeasible solutions. All are infeasible. It can also happen the other way. Like when you are going through generations, you might actually encounter only the feasible solutions. Like you are always getting feasible solutions. Then there is no point in actually imposing a very high penalty on these solutions. So what you essentially do is you decrease the value of lambda. So you gradually go on decreasing. So this kind of takes into effect the actual scenario, what is happening over generations, and you kind of adapt these values. This beta has to be chosen by us, otherwise you just leave it as it is. So this happens when you have a feasible set of solutions. If both of these cases don't happen, then you just keep the value of lambda same. But as you can see, like if you have to actually implement this, then you have to kind of keep track of what is happening over the last few generations and all that stuff. So the simpler approach which we usually employ is something called Dave's approach. The idea here also remains the same. So you have a penalty function which will be equal to the value of f of x if you have a feasible solution. If your solution is feasible, then you don't have any constraint violations. So essentially, you do not want their contribution to the penalty term. So you just take the objective function. If you have an infeasible solution, it can actually, if you have an infeasible solution, then your objective is to drive them into the feasible solution. So what you do, you take 2 contributions. One is the f worst, plus you take the constraint violations as well. Say gj of x plus hk of x. I'm just taking modulus function. You can take square function or it depends. Like you can take any function and see how it actually works out in your particular scenario. But this F worst is what? F worst is basically out of your set of feasible solutions, you select the worst possible one. Like when you rank all your feasible solutions, you'll be having one solution which is worst among them. That is this particular value of F worst. So when you're trying to minimize this particular value of P of X, what it tries is essentially minimize all these three quantities. So this will kind of drive you, like previously when we are trying to minimize it, we are actually trying to minimize the constraint violations, so your infeasible solutions come to feasible solutions. But here, in addition to that, we are also trying to minimize the worst possible solution in the feasible domain. In all the previous methods, what we have done is try to minimize the objective function of that particular infeasible solution, which is anyway not going to be that useful to us, because we are actually interested only in the feasible solutions. There is no point in trying to optimize the value of the objective function for an infeasible solution. In this approach, when we take the worst solution, then if this particular quantity is minimized, then your set of feasible solutions will also move towards your optimal solution. So you have this approach is what we usually use. Now we will see one example of which we have taken previously, like the differential evolution, and see how this is actually implemented. So like, yeah, you have
So
a question.
what is the dynamic penalty? What is the value of gamma? What should we take?
This particular one?
Yeah.
No, this is same as this beta over here.
Yeah.
Like this is similar to the beta over here. It should be some even power. Like if you are just taking a mod function, then it can be even or odd, doesn't matter. But if you do not take the mod function, then it should be some even power.
So if I take parabolic, then I can take any value.
Yeah, if it is parabolic, then you can take any value.
And which one will be better, parabolic or
parabolic is simple to implement. Like you can actually put 4th power, 6th power, everything, but it just increases your computation cost. It's not going to affect that much.
But it always adds because it is a square.
Yeah, square is the minimum you can go with it, right?
So if I take a square, it will simply add.
Yeah, it will simply add.
Add to the penalty function.
Yes.
Otherwise, but here also it is a mod function. Also, it will add only.
Yeah, any function. The idea is same. The idea is with the penalty function, what we are trying to do, instead of solving the problem like the one which we saw in KKT, like if you are using KKT conditions to solve this, you solve them. You get a set of simultaneous equations and solve them. But practical problems, we are having so many constraints, we cannot deal with them in such mathematical rigor. So what we are saying, instead of that, we are actually defining one function which takes contributions from all these penalties, but we do not take the contributions directly. We take a weighted combination of them, and what we are expecting is that this penalty function, when such formulated, when I try to minimize this function, will be equivalent to minimizing my original objective function and also minimizing the constraint deviations. That is what we are expecting. Like finally, when you see all these values over here, like h of x, like if you have a feasible solution, this particular h of x, gj, everything will be 0, and minimizing p of x will be equivalent to minimizing f of x. So the function which you take should not matter to your final solution.
And this t, I think t is the generation, right?
Yeah, t is your generation number.
So what is c? C some constant.
C is some constant. It's something like penalty parameters. So
in dynamic penalty.
It is something like penalty parameters.
But what should be the order of the value c?
That depends on your functions. Like it's the same. All the penalty parameters and all these constants which you are multiplying should be depending on the order of your function. You start with the order of your function and then see how it actually goes up. Like if it is blowing up, then you actually decrease the order of it.
So suppose this first iteration, it is going giving all infeasible. So C can be made high?
No, it doesn't. See, if you are getting already feasible solutions, then this particular Gj and Hj will be 0, right? So whatever value of C you put is not going to affect them if you are having feasible solutions. It's
But
only for
infeasible case.
if you are having infeasible, then you kind of have to like see, that is what we do in adaptive penalty. So here if you see, like if you are continuously getting infeasible, only then you are increasing the value of penalty. It's not like for one generation, it's just all random, right? So you just do not know whether it will increase or decrease. So you will just wait for some generations and see if it is not getting any better, then you increase the penalty.
Sir, can you explain me this KKT condition? This I could not understand.
KKT conditions, okay.
Yeah.
So this is
You can finish this one, then later on you can.
no, like I actually started with KKT conditions today. We'll just go through the same example again once more. So we started with this particular problem where you have to essentially minimize some particular function y minus x, say with these particular constraints. So like graphically, if you have something like this, what we are trying to do is minimize this particular line. Like y minus x, you can say as this particular line, 45-degree line, right? So when I said minimize y minus x, it's basically minimize the x-intercept value. So you know, like graphically, you can see like this will go to this particular value and this will be minimum. How we will go about doing it is first to define some function L of x comma y comma your constants as something like f of x plus u1 g1 u2 g2 u3 g3 and u4 g4. So my original formulation is to minimize f of x comma y. But now what am I doing is formulating a new function L and I'm trying to minimize L. So here you will be getting two equations, dou L by dou x equal to 0 and dou L by dou y equal to 0. So now I have two equations, but I have 6 unknowns. So I will not be able to solve this set of equations. So I am putting additional constraints like u1 g1 equal to 0, u2 g2 equal to 0, u3 g3 equal to 0 and u4 g4 equal to 0. When I impose these additional constraints, then in the original equation, if you can see in this original equation, all these all these terms will go to 0 and minimizing L will be equivalent to minimizing f of x comma y.
This u1, u2, u3, this how to decide?
We do not decide. We will we are essentially, now if you can see, like you have two equations here and four equations here. So we have essentially 6 equations now, and we have 6 unknowns.
Yes, yes.
So 6 equations, 6 unknowns. We'll have set of simultaneous equations, and then we solve all these equations, and then we get the values of u1, u2, u3, u4, x comma y.
Okay, okay. But you are unknown here.
Yeah, you are unknown here. So and u cannot be any value. Like if you see the original function in this particular function, if you want to minimize L and your problem is stated in such a way that Gj is less than or equal to 0. So if you have u value is also negative, and just to put it clearly, we'll just write it here. Say this is my function, say f plus ug. Let's just take one simple example, f plus u times c, u1 times g1, and my original requirement is g1 should be less than or equal to 0. If suppose my g1 is actually positive and I have something, I have when I'm solving the system of equations, I get a value of u1 which is negative. So in this particular scenario, you have a value of u1 times g1 as negative. u1 times g1 is negative. So L value will essentially be like when you define in this particular way with a negative value of u, when you try to minimize L, what will it do? It will minimize g1, and since u1 is negative, it will try to increase the value of g1.
Yeah.
So it is the kind of reverse, like we essentially want g1 to be negative, but the way we have implemented this will kind of drive it in the opposite direction. So we put another condition which says u1 should be
u1
positive.
is also negative.
No. If u1 is negative, then
u1 is also negative, and g1 is negative, then it becomes positive.
Yeah. If u1 is negative,
g1.
Sorry, you were saying if u1 is negative and
g1 is also negative.
If g1 is also negative, u1 is also negative, then it will be a positive value, and then it will increase the value of L, which should not be the case. So we are giving an additional constraint which says u1 should always be positive. Only then minimizing L will be equivalent to getting the feasible domain. So those are these additional constraints.
Okay, sir.
These constraints over here.
Oh, yeah, U1 should be always positive.
Okay. Now once we have the conditions, we just write down the equations. So the first equation is dou L by dou x equal to 0. We get this set of equations. Similarly, dou L by dou y equal to 0. We get another set of equations. And then we have all these constraints, u1 times g1, u2 times g2, u3 times g3, u4 times g4. All of them should be equal to 0. So then we solve one by one. So in this particular scenario, if you add these equations 1 and 2, you get something like u1 equal to u3. And similarly, if you subtract this 1 from 2, you get another equation which says u4 minus u2 should be 2. And we already know, like, from the u4 and u2 can only be some positive numbers. So u4 should be greater than or equal to u2 should be greater than or equal to 0. And if you see all these equations from 3 to 6, they will essentially boil down to these conditions. Either u1 equal to 0 or g1 equal to 0, or you can have both of them to be equal to 0. Similarly, u2 g2, u3 g3, u4 g4. Now out of all these possibilities, you need to find your particular combination which gives you the right results. So say suppose I'm just starting with, say, u1 equal to u3, like this is my original equation, u1 equal to u3. So I'm saying if u1 equal to u3 equal to 0, then, and u2 is also equal to 0, from this original equation u4 should be 2. Since u4 is 2, this particular condition is not satisfied, so this particular condition has to be satisfied. So x minus y minus 1 equal to 0, which gives me a value of y minus x equal to minus 1. So in this particular scenario, all my KKT conditions are satisfied. Like you can see, like u1 and u3 are 0. So essentially 3 and 5 are satisfied. u2 equal to 0, so 4 is satisfied. And this particular condition is there, so this is satisfied. And this we have kind of obtained only from these equations. And these two equations are essentially my dou L by dou x equal to 0 and dou L by dou. So it kind of satisfies all the equations. So this is my optimal value. Now it can also happen the other way. Say suppose you do not have, you have u1 equal to u3, but they are not equal to 0. If u1 and u3 are not equal to 0, then this has to be satisfied. So we just take those two equations. And as you can see, like these two equations are essentially a set of two parallel lines. So you do not have any solution for that, which will give you the value of x comma y. So with this, you are not obtaining any solution. Like if you can try with any other possibility, like that will eventually lead to some set of parallel lines and will not give you any solution. The only solution is this particular case. So this is how you do with KKT conditions. I hope it is clear. You have any question with this?
Thank you.
Okay.
This long back it was only Kuhn-Tucker condition. This now it is KKT, right?
Long back in the sense when they invented it that way.
Yeah. No, I think I had Kuhn-Tucker condition.
Kuhn-Tucker conditions. Let it be. Yeah. So where were we? We were at this particular example. This is the previous same workbook which we used for differential evolution. Now instead of there we have kind of done our like in our original scheme we are trying to minimize objective function, but now what we are introducing is a penalty function. So like we will be using the Dave's approach. So we will be using this particular last approach that we have discussed. So this is the approach we are going to use now. So the first step in any evolutionary computation technique is basically you initialize your random population. So I have initialized to some values. So after initializing the values of x comma y, the next step is to calculate the objective function. My objective function here is y minus x. So I've just done that. So I've got all the values of f of xy. The next step is to calculate the constraint violations. So I have 4 constraint violations which I've calculated over here. Now comes the penalty function. The penalty function is defined in this particular way. I have used the Dave's approach. So that is equal to f of x comma y if you have a feasible solution.
Yes.
If you have an infeasible solution, then you kind of take the worst in the sense worst of all the feasible solutions, plus you just take I'm considering here square function like alpha equal to 2 and also beta also, like both of them to be parabolic functions, which cannot be the case. Like you can take up with any values, and with this approach I am not using any penalty factors as such. I'm just using the value of 1, since like you can see here all are of the same order more or less, around 0, somewhere between 0 and 1. So I'm just like it's -1 to 1, and the function values will also range around somewhere between -2 to 2. So I'm kind of considering all the penalty factors to be 1. So the steps are like this. So first I evaluate the value of f of x comma y using x and y, and then once I got all the values of g1 through g4, let us go one by one. So for this first one, g1, g2, g3 are all negative. All these 3 values are negative. Our original problem when is formulated in that particular way where gj should be less than or equal to 0. So all these 3 are feasible, but when you see g4, it is positive value, so it is an infeasible solution. So when you are having infeasible solution, the objective is, the way is you essentially have to first get the f worst. How do we go about getting f worst? Is now first I need to identify the set of feasible solutions. So my feasible solution should be the one where all g's are essentially negative. So this is one solution. This is one solution where all of your g values are negative. All g values are negative, so this is one feasible, and then you have this again is a feasible solution, and this particular one is also a feasible solution where all g's are negative. Out of these 3 feasible solutions, this is one feasible solution. Let me just highlight in a different color. This is another feasible solution, and this is another feasible solution. So we have 3 feasible solutions. Out of these 3 feasible solutions, we need to select the worst feasible solution. Since our objective is actually to minimize the value of x, the maximum value will be the worst solution. So the f worst will be a value of this particular one. So this is my, yeah.
See, suppose there are 5 gj, okay,
Okay.
and 3 hk's.
Okay.
So all should be satisfied.
Yes.
To make it, to consider it feasible.
Yes.
Suppose out of 5, 4 are satisfying.
Yeah, like the
only 1 is not satisfying.
Even if 1 is not satisfied, then it is infeasible.
Infeasible.
Like the point will be just outside the feasible space.
Thank you.
Okay. Yeah, we have calculated the worst possible value as 0.77381, or basically that is 0.774. And then we use this particular form to obtain the value of penalty function over here. So like we repeat it for all these values, and then we got a set of penalty values. Okay, we also happen to have another feasible solution. This also is a feasible solution. So we have 4 feasible solutions here. Okay, the next step in differential evolution is to calculate your mutant vector. So what we do is we essentially generate 3 random vectors, and from them we use this particular formula to generate your mutant vector. So if we have, in this particular case, we essentially have 2 variables in the sense x and y. So we use the same random numbers to get a vector for x and y, similarly x2, y2 and x3, y3. And from that combination, we generate a vx and vy for the next iteration. After that, the next approach is to get the trail vector. The trail vector also is a similar approach where you essentially have a crossover probability. In this particular case, I'm considering a crossover rate of 0.5. And here it is a 2-dimensional problem. The previous example which we considered is a 1-dimensional case. Now we are having 2 variables. So we use the same formula. Yeah. So first I generate some random numbers. If the probability is less than or equal to 0.5, then actually like we use this particular condition. The second condition, as we have discussed previously, is essentially to increase the probability of selecting the mutant vector. And then once I kind of get all the values of trail vectors ux and uy, the next step is essentially to evaluate the fitness of these. So I again do the same. I obtain the objective function values and similarly all the constraint values, and then the penalty approach like is the same here. You get the f worst. F worst is essentially you obtain all your feasible solutions in this. So if you can see, we will go through them. The first one, G4 is essentially positive, so that is infeasible. For the second one, all of them are negative, so that is a feasible solution. Third one, G3 is positive. For the fourth one, all of them are negative, so that is another feasible solution. And for this one is again third one is positive, so it is infeasible. For this particular solution, all of them are negative, so this is a feasible solution. And in this particular second, again all of them are negative, so this is feasible. In this we have G4 to be positive, so this is infeasible. So out of these highlighted four solutions, the worst possible one is 0.46, so we are taking this particular case, that is the F worst. So from that we calculate all the values of penalties over here. Once we get the penalties, the next step is actually going to select them. How do we go about selecting them? We will just first list down. So these are my original values of x comma y. After obtaining the mutant vectors, and from them we finally get the trail vectors. So these are the trail final vectors after both the operations. So in selection, what we do is essentially you select that particular individual whose penalty value is like it's the greedy approach. So your final vector, say I am saying it as say x prime or y prime or any, or we'll just put u prime. U prime will be the one obtained after trail vector, like it will u is your trail vector if and only if the function value, or in our particular case is the penalty value of particular value of u should be less than penalty value of x. X is my original solution. Otherwise you just take the value of x. Let's see in one particular case, say we will stick to the first case. In this particular value you have a value of 1.095 and 0.639. So the trail vector has a lower value of penalty, so you should be selecting the trail vector from the first for the first individual. So this is my trail vector coming in the first individual. Now let us see the third case. In this case, the original vector has a value of minus 0.975. The new vector has a value of 0.483. So I will be choosing the lower one. So this is so I should be having this in my solution. That is what we have in the third solution. Like you can see in this last case where the original one has a value of 0.39, while the newer solution, like the trail vector, has a value of 0.843. So the minimal is there in the original one. So I will go about with the original one itself. So this is what I get in the previous phase. So now you have a mean value of around 0.005 and a best value of minus 0.95. Like we have already solved this problem using KKT conditions, and we got a solution minimum value of around minus 1. The minimum value of I minus x to be minus 1. Now let us kind of iterate through this to see whether we'll actually get to the same solution or not. We'll just iterate in the sense we'll just copy these values into these values. So you can see like mean value has kind of decreased even further, and maybe after some iterations we'll actually converge. So it kind of, as you can see, like the mean value is gradually decreasing, but the best value is still minus 0.975. So if we can kind of iterate it even further, we might actually, so minus 0.781, it's kind of improving. So the minus 0.835 and minus 0.975. So we can repeat it again. So it kind of remain the same. See, the mean value is gradually approaching the best value. Now you can see like the best value is already, like previously it used to be minus 0.975. Now it is kind of changed to minus 0.979. The best value remained the same, but the previous value was kind of decreased. Now if you kind of repeat this gradually, you will eventually reach a value of minus 1. We'll just do it quickly. See, the value has already reached minus 0.998. if you iterate even more, you will like it can kind of already reached a value of best value has already reached -1. So if you go through maybe like 2 or more generations, even the mean value will kind of reach the actual value. You can just see that. Like maybe after 2 generations, in the interest of time, I'm not doing that. But if you just do 2 more iterations, you might actually get the mean value equal to best value, and all these values will actually be the same, and then you can stop your iterations. That will be your stopping criteria.
Excuse me.
Yeah.
See, here you know the solution beforehand, so you are waiting to converge to -1. But if you don't know the value beforehand,
Yeah, even then it is going to be same. Like after like if you repeat it again and again after 2 or more generations, the value won't be changing, right? The best value will still remain the same. Even the mean value will converge.
Termination criteria should be mean and best. That should be close.
No, it's not about me and best getting close. That could be your criteria, but the criteria is essentially like as you go through generations, these values should not change. Like at t generation, you have some value of best, and t+1 you have some value of best. What we are essentially saying is this bt+1 minus bt should be less than some tolerance, some epsilon. And this cannot be actually 1, or maybe you can actually go like some 5-6 generations and see like this particular condition is getting satisfied like continuously for like first to second, second to third, like up to 5 generations. Then you can kind of stop it. There is no point in essentially running to another generation.
Okay. Even though the mean value is different.
If you would have reached such a case, the mean value and best value will be more or less equal.
More or less, okay, sir.
Yeah. Otherwise, like you have not reached convergence. Like it will keep on oscillating in your generations.
Yeah.
Okay.
Thank you.
And now we'll come back to our original case. Now we'll take up another problem. We'll discuss about something called multi-object optimization. That is what is being discussed over this week of lectures. So essentially, we in practice actually encounter problems which have multiple objectives. So we will just see one example. Say suppose you have some function, something like minimize y by x, and at the same time you also have to maximize x. So here you have 2 different objectives. One is to minimize y by x and second is to maximize x, and you have some variable bounds. Say in our particular case both x comma y. Range between 1 and 2. So as you can see here, you do not have any problem as such. So if you want to minimize y by x and maximize x, then you essentially have only one solution. That is a value where let me just draw graphically to see what is happening here. So this is my coordinates and my x and y, okay, are just positive. So let me just. So this is my feasible space. Like this is my domain, and what I'm saying is basically maximize the value of x. So you should be somewhere along this line. So you should be somewhere along this line to maximize the value of x. And when you want to minimize the value of y, this is your maximum value of y. So if you want to minimize it, your value will be somewhere over here. So essentially, you should be somewhere along these 2 lines. The point of intersection of these 2 lines will give you the maximum value of x and minimize the value of y by x. So you kind of got a solution to it immediately. Like these are the problems which you call the objective functions are not basically trying to conflict with each other. And in practice, we usually not encounter these problems. What we have is something like both the objective functions will be competing with each other. Something like this scenario where you want to minimize y by x. At the same time, you want to actually minimize the value of x as well in the same domain. So if you have a problem like this, we'll just see what is actually there. What I have done is like just taken the values of x in this particular direction. Like these are the values of x, and along this I am taking the values of y, and these are the values of x. So the domain is 1 to 2. So I've kind of split it into intervals like of around 0.2. So like 1, 1.2, 1.4 up to 2. Similarly for the values of x. For each of them, the first column is essentially the first function y by x, and second is essentially your second function f2 equal to x. So when I just calculated these values for all these in the entire domain, you can see like let us stick to one particular row. In this row, as you go from top to bottom, your value of f1 is essentially your first objective, is decreasing, but at the same time f2 is actually increasing. But our original objective is essentially to decrease both the functions. So it's like one of the value is decreasing at the expense of the other value. So you cannot actually solve this problem as such. Like you cannot say whether this particular solution is actually better than this particular solution. Say that we'll consider these two highlighted case. Let's say the top one is solution 1 and the bottom one is solution 2. We cannot right away say whether solution 1 is better than solution 2 or the other way around. That is because the problem formulated in this particular way cannot give us any information about that. So this is something we need some information which is beyond this problem statement to help us guiding decision where choosing the which of these is better than the other. So that is what we call the high level information. And these are the classes of problems which you usually encounter, and this is called a multi-objective problems. So we'll just start with the mathematical formulation is essentially the same. The first step is the same, more or less the same. So like you will be minimizing some function f1, but in addition to that, now we'll be having other functions, say f2 of x, so on. Say suppose you are having m functions, fm of x. All of them have to be minimized simultaneously and subject to the same constraints as before. Say you have some inequality constraint gj less than or equal to 0, hk equal to 0, and you are having some variable bounds x of l less than or equal to x less than or equal to x of upper bound. So these are these conditions are still the same. The only additional effect is this. So how do we go about solving this? There are essentially two different approaches to this. Like we have discussed previously, you cannot solve them right away. You essentially need some high level information to identify which of them is actually correct. So the first approach is, the idea is simple. When we have, it is something like the previous case of introducing a penalty functions. So like when you have a set of constraints and you have an objective function, what we try to do is to somehow get a single function. Like most of the methods even we discussed previously kind of deal with unconstrained optimization problems. So like we kind of know the techniques to solve a problem which says minimize f of x within some variable bounds. Those are the kind of problems which we have focused previously. So we always try to kind of format our own problem into that particular framework, so it will be easy to solve. The penalty function also does the same. You have so many inequality constraints. What we try to do is when you introduce a penalty function, all of these come into one single function, and when you try to minimize this function within the variable bounds, it will be same to the previous case of unconstrained optimization within the variable bounds. So here also the first approach will be similar. So when you have so many objective functions, you kind of come up with a new function, say some capital F of x, somehow taking into factor all these values of f of x. So some weight functions times fm of x, where your small m will actually range from 1 to capital M is your essentially total number of constraints. So when you formulate your problem in this particular way, then you have the same, again with the same inequality constraints and equality constraint and variable bounds. And then again you kind of define another penalty function p of x to kind of incorporate this plus this into this particular function, and then you go about solving it in the same techniques which you have developed previously. So like here again, what should be the value of wm is essentially the weight you are giving to each objective function. This we do not know ahead with this particular problem formation. This has to be given by the designer as such. Like just to give an example, say suppose if you are making some product, your objectives could be like you want to minimize your cost, and maybe you want to maximize your quality. And usually when you want to maximize your quality, you might have to do so many particular tests, and you might have to have more precision or more accuracy in kind of the equipment you are using. So that will kind of try to increase your cost. So how will I know like how will I know the impact that I should be giving to each of these cost and quality should be given by the one who is actually making the decision. Maybe the particular person would have told you, say, this I'm denoting with FC and this I'm denoting with quality, and he might actually know, like from customer reviews, that say suppose when you if you minimize some function, like giving equal weightage to both of them, like if you do not know anything, the simple approach is like you assume like both of them are equally important. So like that is a simple case we can do, but usually what we encounter is like you might be in some lodges, you might have think like the cost is more important to me, then you can have to give more weightage to cost, and you kind of decide the value of the other one less. Like you can come up with any values of WM, but the only condition is like all these WM should be within the values of 0 to 1, and the sum of all of them should be equal to 1. So it's like you take a weighted average of all the objective function values and get the actual value of f of x, and then you go about solving with the same unconstrained optimization problem. That is a single objective unconstrained optimization problem. But like that is one technique to about we can use to solve, but we will be discussing about some other techniques. The next technique is we actually take all these problems and simultaneously solve them. How do we do that is, say suppose you have let's stick to a simple example where you have just two objective functions, f1 and f2, and you have say some variable space x1 and x2. So when you essentially vary the value of x1 and f2, you get several different values, several different possible solutions, and each one of these solutions will give you a value of f1 and f2. So So the first one is what we call the variable space. The second one is your objective space. So this is our basically our search space. So we vary the values of x1 and x2 and obtain different possible solutions. And for each of these possible solutions, we will have some value of f1 and some value of f2. Then we get something called objective space where we populate this. Now, when you want to make a decision, what you essentially need is this objective space. So like in previous of single objective optimization, we don't have anything something like objective space, but now we will be having this objective space. Now, out of all these solutions, we want to identify that particular solution which is useful to us. How do we go about doing that? So you can see if our objective is say minimize both the functions, minimize f1 and minimize f2. So or just put simply like you can kind of make a boundary over here and say this as your objective space. Like this particular boundary has all the solutions which encompass your objective space. And you redraw it to kind of give you better clarity. Say this is your objective space, and your objective is actually to minimize f1 and minimize f2. So the idea is like, is any point, can we say whether one point is better than another point? Like how can we compare two different solutions in this objective space? That is the whole idea we will be having when we discuss with multi-object optimization. The first concept we come up with is what you call a Pareto front, which essentially says that, okay, but before that we will start with something called a dominance. Dominance is essentially like, say suppose f1 and f2, I have one solution, say point A, having a value of 1.5 and 2.5, and say I've got another point B, say this is some point A, and say point B is here, which has a value of say 2.5 and 3.5, something like this, and then you have another point C over here, say something like 3.5 and 0.5. So when you see all these 3 points, for the first 2 points, it's like we can clearly say if whether A and B, like if you want to compare A and B, which one of them is better. So if you see B, like both the values of an F1, F2 of B are higher than the values of A. So B is actually kind of worse than A. I'm just using greater here. I mean by greater than symbol is essentially like one particular solution is actually better in terms of the purpose we are actually trying to solve, minimize both F1 and F2. So like A has, so we'll just use less than, in the sense it has kind of a minimum value, so we'll just stick with less than. So A is kind of a better solution in the sense it has a lower values of both F1 and F2 compared to B. But now when you want to try to compare A and C, if you want to compare A and C, you can see like the value of F1 is minimum in A, but for C, F2 is minimum. So you cannot right away tell whether A is better than C or not. Like, this is the idea we are going to use. This is something we denote with something called dominance. So if you can kind of establish a relationship saying one is better than other, that is, then you call them to be dominated solutions. And the other one is essentially non-dominated. And our whole idea in multi-object optimization is essentially to get a set of non-dominated solutions. Because when you have a set of dominated solutions, there is no point. You actually need the minimum of them. So you just take out of all them, which of the best, you just take them. So in these solutions, we essentially pick A and C to be non-dominated solutions. So similarly, you will be having so many non-dominated solutions. So when you kind of take all these non-dominant solutions and make a locus of all of them, you get something called a Pareto front, which you can kind of see in this particular image itself. So see, you can.
Excuse me, sir.
Yeah.
Why it is called non-dominated?
Like you can see
Because
in A and
we
C.
don't know how close we are.
Sorry, I didn't get you.
This we don't know that it is we are close to the solution.
Like we do not know how much weightage to give for each of these functions, right? Like if you see A and C.
Yeah.
If you see A and
Yes.
C points, like in one objective function A is better, in another objective function C is better. So which one is better out of these two, I cannot say, right? Unless I know
Yeah.
how much weightage to give to each of them.
So non-dominating, what is the meaning of non-dominating?
Like one solution is, you cannot compare both of them, so you are essentially calling them non-dominated. Like dominated is essentially like one solution is dominating other, in the sense one is better than the other.
Okay, had this A been 1.5 and 1.5, can we call it dominated one?
If A is 1.5 comma 1.5.
Can we call it, suppose 1.5 and 0.5.
A is 1.5 and 0.5.
Now it looks that it is dominating.
Now in terms of F2, then they're kind of, then you have two essentially, then you call it strict dominance and weak dominance. So strict dominance is essentially the case when they should not be equal. One should be definitely better than another. But here you have an equality. But you can see like when you have both of them to be equal, then A and C are kind of weakly dominant, right?
Okay.
A has the function value of F1 which is greater than C value, right? Less than C value. So A is better than C in that particular term.
Yeah.
So you essentially have two different cases. So the first case is like all the functions of, say suppose, let me put it formally. So you have say two values I and j. What we are saying, I should be greater than or equal to j. I mean better, or for us in minimization problem, objective value of I should be less than or equal to objective value of j, and this should happen for all the objective functions, m equal to 1 to m, and this is first condition. Second condition, there should be at least one particular case where this is strictly less than the second one, at least one particular case, which is not happening when you, like if you kind of relax the second constraint, then you can kind of say like both 1 and 2 are kind of non-dominated, dominated. But if you remove the second constraint, where you essentially say if it is strictly less than, I do not want any equality in between them, you say it is dominated. Like it depends upon your definition. I hope you got it right, or did I confuse you more? Hello, am I audible?
Yes.
Yeah, clear, right? Yeah, what we were discussing is essentially when you have this set of non-dominated solutions, you just take all these non-dominated solutions and you can get something kind of a locus of all these non-dominated solutions. Then what you get is something you call a Pareto fund. So in this particular case, so I'm just removing the solutions in between. So if you have your objective space as this, when you want to minimize both F1 and F2, your Pareto front will more or less look something like this. So this particular highlighted region will be that portion of your particular case where you will be reaching minimum. But you can have other scenarios as well. Say suppose you want to maximize, you want to maximize F1 and minimize F2. Then in that particular case, like you want to maximize F1, at the same time you want to minimize F2. So your Pareto front will be somewhere here. And again, this cannot be the only case. You can kind of want to maximize both F1 and F2. In that particular case, your Pareto front will be something like you want to maximize both F1 and F2. Like this is the cases where your constraints are driving your problem. So in your objective space, you will have something like this. And like that is the particular reason where your both functions are kind of maximized. And you can also have the other scenario where you want to minimize this particular value of F1 at the same time maximize F2, and in that particular case you'll be kind of ending up in the other quadrant. This particular region will be your region where your Pareto front will lie. So these are essentially kind of to give you an idea of where the Pareto front lies. But the problem is, let's return to the original problem. How do we go about solving this particular case? So once we got the idea of what a dominated solution is, the idea is to essentially get a set of solutions which are non-dominated. At the same time, the second parameter that is of importance is like just not identifying whether domination is there or not. There should be enough diversity within the domination. What I mean by diversity is, say you have, say I have some objective function like this, and this is my Pareto front. I can have so many solutions in this particular, like two particular cases. So I can have solutions something like this. My objective is to identify the entire Pareto front. But if I have solutions, only the marked ones as solutions, then only small portion of the Pareto front is occupied. So this is not what I want. What I essentially want is to make the solutions occupy the entire region of the Pareto front. So if it can occupy the entire Pareto front, then I'm kind of having a set of solutions which are more diverse in the nature. So now we come up with two concepts. One is essentially, the first one says the dominance. So I need to have dominance in this. I need to have non-dominated solutions to be able to identify the Pareto front. And second one is actually diversity. So I need the solutions to be as diverse as possible so that they can span the entire Pareto front. So how do we quantify this? Like how do we put it in mathematical framework so that when we implement it in the actual approach, we will be able to solve it. So the ways are like, for the dominance, we have several methods. So we have something called rank and dominance count method and dominance depth. We'll go through one by one to understand what they are. So let us go through one example to see what they are. Say suppose you have some values of F1 and F2 like this. Like we have a two function optimization. Sorry, a multi-objective optimization problem with two objective functions F1 and F2, and there are 8 individuals in the population. So like they are numbered from 1 to 8. If I make a plot of this in the objective space, it appears something like this. Like each individual is denoted by a dot with a particular point of the objective functions. So in the first approach, rank method, what it essentially says is what you do is to identify how many points does a given point dominate. So like how many solutions or points are dominated by the given point. Plus you add a 1 over to it. This will kind of give you the rank. This will kind of tell you essentially like how many solutions are there that are kind of inferior to the one that I'm currently like basically it's like the ranking scheme which we are having. Let's just see the example. So if you consider the first point, this particular point, how do I obtain how many solutions are dominated by this point? Or like domination, if your objective is essentially to minimize both F1 and F2, if you want to minimize both F1 and F2, ideally your objective is to kind of have some point over here. So if you are having any solutions in between this particular point and this particular region, so in this particular region, if you are having, if there is any solution in this particular region, and that say suppose if you have a solution here, this particular solution will dominate this solution for sure, because it is having a value of both F1 and F2 which are less than this particular values of 1.8783 and 4.311. So the idea is simple. You just draw two lines over here and one horizontal and one vertical line joining that particular point, and see how many solutions are there in this particular rectangular region that is formed. This number of solutions will give you how many number of points it is dominating, plus you add a 1 to it, and that will give you the rank. So for the first point, if we draw the box, we essentially don't have any points in between. So the rank of this is 1. Now we will see this particular point. So even in this box, we do not have any solutions. So the rank of this will also be 1. Now if you happen to see this particular point, give me a second. Yeah, we are seeing like this particular point has a rank of 1. Even this particular point has a rank of 1. Now when you happen to see this particular point, in that box there is actually 1 point which is dominating this. Like if you can see, this particular value of 3.28 is actually less than the value of this particular point, and even the second objective function is actually much greater than the value of 1. So this is actually being dominated by 0.1. So this will be your second, this will be of rank 2. Similarly, if you go through one by one, for this point there are actually 2 points which are dominating. So this will be of rank 3. And for this point, you can see like this particular objective value is less than this. 3.532 is actually greater than 1. So this particular point is actually dominating. Even this particular point, if you see, is not dominating, but this again will dominate it. This will again. So there are 3 points which are actually dominating this given point. So its rank will be 4. Now if you happen to see this particular point, here again, if you draw the bounding box, you have three points in that rectangle. So the rank of this will be 4. Now when you see this particular point, here again, if you draw the bounding box, there are essentially 1, 2, 3, 4, 5 points inside it. So this rank will be 6. And when you go to the last point, all points are actually dominating that particular point. So there are 7 points. So this rank will be 8. So this is how you compute the rank of each individual. So you can see like from our original definition, like Pareto front is actually consists of solutions, the set of solutions which are non-dominated, in the sense which are essentially having the rank 1. So if you can count the rank of this, these 2 points will be actually lying on the Pareto front, and the remaining points are essentially being dominated by these 2 points. So this particular metric will kind of help you to identify those points which are actually lying on the Pareto front. But there is actually one, when you're actually implementing it, you can kind of encounter some discontinuities. Like you can see in this particular point, like you have rank of 1, 2, 3, 4, and 5 is actually missing. You don't have any individual in the solution which has a rank 5, and then you have 6, and then you don't have any individual with rank 7, and then again you have 8. Like you kind of get some discrete. So when you want to assign ranks ascend ranks in the sense you kind of define 1 to 8 individuals as here, and you want to keep ranks, you should kind of have a data structure which kind of allows you to kind of put two individuals into the same rank. That is kind of should be taken care during the implementation stage. But now this we'll just stick to the fundamentals, like how do we calculate the rank. Like this could be one approach. The other approach is essentially you do it the other way. Instead of counting the rank, we do something called count. Here what we do for the same problem, if you want to minimize f1 and you say you want to minimize f2, like one of them is f, say this is f1. Actually I have plotted it this particular way and this is f2. What we'll do, earlier we focused on this particular point. From here we kind of calculated, but now what we will do is essentially calculate from the other end. I mean the other diagonal of this particular form, and we say in this particular way, this will kind of tell us how many points are dominating this one. Like in the rank we kind of told for a given point how many points the given point is dominating, but now we will be saving the other way around. So this will be more or less the rank minus 1. So if you can see like this particular point, you don't have anything in the box surrounding it. So we'll start with 0. And when you go to the next point, you essentially have one point that is like this particular point is actually dominating only one point in this particular set of individuals. So this has a count of 1. Now if you see this particular point, the third point, it is kind of dominating 2 points. So the dominance count is 2. Now if you happen to see this particular point is again dominating 2 points in the solution. So the dominance count will be 2. Again for this particular point you have 3 points, it is dominating 3 points. And again for this particular individual, this is dominating all the 5 points, so the count is 5. This particular point will dominate 6 points and this particular point will dominate all the 7 points. Now 1 second, sorry, this particular point 1.783 and sorry 4.311, 4.334, this will be above. So it will dominate only 2 of them. It is not 7, sorry. The dominance count of it is 2. Yeah. So now here if you can see like previously when we used the rank method, the Pareto front essentially has 1 and 1. But now here you have 2 different ranks. I mean 2 different count values. But both of them will lie on the Pareto front. So one of them is kind of dominating 6 solutions, but the other one is dominating only 2 solutions. So if you use this particular approach, you will kind of end up in a situation where you cannot directly identify the Pareto front. Like when you have these 8 solutions, you cannot right away tell which of these 8 solutions will actually constitute the members of the Pareto front. So we do not actually encourage to implement this particular approach. There is another approach which will kind of give you even more information. That is the depth approach. Here what we do is recursively apply the same method, the rank approach. So that we'll get the layer by layer. Like if you are familiar with the kind of graphical algorithms, this is something like the breadth first search. So it's the same, we start with the rank approach. So we'll stick to the lower left corner and individual by individual we will go. So for this first individual, you have a rank of 1. And then again, you see even this individual has a rank of 1. This individual, when you go, is getting a rank of 2. So what we do is essentially, we do not give it a number of 2 directly. We will stop with this, we'll stop with these 2 individuals. And then we will say, this constitutes our first rank. I mean, this constitutes our first rank, front one. And then we'll remove these 2 individuals from the solution and again start our process. So this particular, only this individual, like after removing these 2, this has a rank 1. This has a rank 2. So the second front has essentially only 1 individual. So this will be my front 2. Now again, for this individual, I have essentially, like I remove that again. So once I have removed all the 3 solutions, for this particular individual, in the rectangle, I do not have anyone. So this has a rank of 1. Now for this one, the rank is again 1 since there are no individuals. This has a rank of 1. When I come to this this particular point, I will be having one more point. So this will be having a rank 2. So I will stop at this and draw another front. This is a third front. Likewise, you go on for the next point again. If you happen to see this particular point, it has none of them. So it will be of rank 1. So this will be getting dominated by, so this will be of rank 2. So you stop at one more front here. So this will be front 4. And this one point will be front 5. and this will be front 6. Like if you do this depth approach, you can kind of get the different fronts at various depths, which will kind of give you various Pareto fronts at various levels. From this, whatever is the first level is your Pareto front. Once you get the Pareto front, like the previously when we started with multi-object optimization, we told like the first step is essentially to obtain a set of solutions which are non-dominated. Those are the ones which lie on the Pareto front. Once I got the Pareto front, the next step is to essentially kind of know whether they have enough diversity in them or not. That is what we have discussed previously. Like we need to have the individuals which are diverse enough. Now, how do I quantify the diversity? So let's say we have something like this. We want to minimize F1 and minimize F2. And you have some solutions. Some solutions say this is some ith solution and this is some jth solution. So we try to get some measure which kind of tells us how close these 2 points are. So I define some metric Dij. That will measure the distance between points I and j. And once I know Dij, then I will kind of tell, okay, if Dij is within certain threshold. So say I'll get some thresholds around each of these points. Like once I fix a threshold, that will kind of define the region within which the next point should lie. And if these 2 points are such that if this is my first point with some certain threshold, and this is a second point with certain threshold, and if both of them are non-overlapping, then it means that they're already spread enough that, or in other words, they are diverse enough. But it can also happen that the 2 individuals are close together, so that both these regions will be overlapping. In this particular case, this is kind of diverse enough. This is a case where it is not diverse. What we essentially want is this kind of solutions. So we want to identify, okay, I got the Pareto front, the set of solutions in the Pareto front. The next thing is I define a metric which will kind of tell me how diverse they are. If they are already diverse enough, then I'll be good to go ahead. If they are not diverse enough, then what I will do is essentially generate new solutions which are diverse enough. You have any question?
I think this diverse means that 2 solutions, their difference is more.
The set of
In left
non-bounded
side,
solutions should be far apart.
A diverse, you have shown that 2 solutions, they are far apart, so they are diverse.
Yeah, diverse in the sense they're far
Is it
apart.
so?
Yes.
Okay, and right side they are very close, so not diverse.
Yes.
So we should take diverse or not diverse?
Diverse.
Diverse. Okay, thanks.
Okay. Or maybe we'll go through one example to understand how we actually do it. So like it's the same previous functions like f1, f2. These are my set of objective functions. So just understand how we actually do that. First step is essentially to get the value of Dij. So we kind of calculate the distance between each point to every other possible point in the feasible space. So this is my I and this is my j. So to calculate Dij, what I'm essentially doing is I'm just using the Euclidean distance for the objective space, in the objective space, the distance in the objective space. So when you are having f1, I corresponds to that particular individual. So let me put it in superscript. And for that, minus f1j, f2i minus f2j. This I have to do for all possible combinations of I comma j. Then I get this entire matrix of Dij. So with this you can see like along the diagonal elements it should be 0. Like essentially it's like D11 is essentially distance between 1 and 1. So they will be anyway 0 and it will be a symmetric matrix. So you need to essentially do instead of n square, like when implementing you can kind of optimize that. We'll not go into details of that. But once you get the matrix of Dij, the next step is essentially to define a parameter called sigma share. The sigma share is essentially it's a kind of a parameter that user has to give, which will tell how close. Like in our previous example, this is the sigma share is something like the radius of this particular region that surrounds the value of x or that particular Dij value. So how much distance is acceptable to you to say whether it is diverse or not. So here I am just see if you can see the values over here, they are kind of ranging from 0 to around 5 or something. So I've taken a value of sigma s around 1.2 to say whether it is diverse or not. The next step is something called, we actually need to count it. So we define some parameter called sharing factor. It essentially depends on ij.
How you have taken 1.2 that sigma value?
No, I've just taken some value for the sake of example. This kind of depends on how your Pareto front is. Like we cannot say it beforehand, but if you can see here, all the distances are in the range of 0 to 5, right? Like your objective function value, the maximum value is 5, and the minimum value can approach is 0 or something. So I'm just taking like if a spacing of around 1 should be sufficient to get, if I am having 8 points and if they are separated by a distance of 1, more or less it will cover the entire front. I'm just assuming it that way. It cannot be. Like to put it simply, say you are having a front like this. What I'm saying is like I want to have the points at least spaced by a distance of 1.2 so that they'll span this entire curve. Like I'm having only 8 points, right?
But earlier you have shown many fronts. So which one to take?
This works only like 1 second. Let me just earlier in the sense this particular one you were saying.
No, before that you have shown many fronts. Means
okay, in the case like minimize f1, maximize f2 in that particular way.
Yeah.
No, that particular thing does not affect this one. You can see like the front can be in this particular way or it can be of any other shape. Like can be of the other shape as well. Can be something like this. Even then the objective is like you will be having your solution somewhere on the front, right? Like we are assuming like we already got solutions on the Pareto front. Out of these solutions, we want to identify whether they are diverse enough or not. So what I am saying is like I'm saying when you are getting solutions, like you in evolutionary computation, when you are randomly generating something, you will always get some solutions which are non-dominated. Out of them, they should be sufficiently far apart so that I'm saying a factor of 1.2, and when I'm having 8 solutions, if all these 8 solutions are at least 1.2 distance apart, the distance between the minimum and maximum will be sufficient enough to cover the Pareto front. That's what I'm assuming, which will kind of change from problem to problem.
Okay.
So once you define the value of sigma x, the next step is you basically calculate the sharing. The sharing is essentially your overlapping region, how much it is essentially overlap. You get something like this. So you will get some finite value only if your distance is actually less than your sharing value. Otherwise, you just put the contribution to be 0. Basically, only when you are overlapping, you need to count that. If it is non-overlapping, then you don't have to consider that. You don't have it to be contributing to your sharing factor. Like once you are done with calculating the sharing factor, the next step is essentially to calculate your niche count. I'm just denoting it by NC. Just NC. This NC will kind of NCI for each individual. I will be calculating some count which will kind of tell me how much close it is to the other points. So it is something like do a summation of all sharing factors, but summation over only j. Say like once I got all the Dij values, so here what I do for each individual, say we'll just take the example of this particular case of I equal to 1 and j equal to 2. For I equal to 1, j equal to 2, I have a D12 value of around 0.594. My sharing parameter value is 1.2. So in this particular case, like the distance is actually less than sharing, so they are kind of overlapping. So what I'm saying, I'll take this contribution as 1 minus. So this particular value is getting reflected here. So this I kind of repeat this for all individuals. Like I'll consider the same point 1, then I'll calculate the distance for 2, 3, 4, all these points up to 8, and then I do a summation of all these things. Then I get a value of NCI. So this particular value of NCI will now tell me like how that particular point is getting influenced by the closer points. So if you have more number of points that are closer to the point 1, then you will essentially have your sharing parameter to be high, and this value will be closer to 1. Sorry, the other way around. So if you're having all values very close to that particular point, you will have a very higher value of sharing parameter, and you will end up having a higher value of NCO5. So if you repeat it for all the set of individuals, these are the values of NCI you are getting. I think, okay, 1 second. It is defined in minus, so it will be the other way around. So when you are having if your Dij is less than or equal to sigma s, so the points are very close together, so this particular value will get decreased, so your sharing parameter will be increasing. So when your sharing parameter is increasing, your NC value will be increasing. So your this particular value will also increase for the particular case when the points are very close together. I hope now it is clear.
Is there any good reference to understand it better?
There is actually one book that is posted in the lecture series, if you happen to see the professors. He has actually given one link where it is himself explaining that. If you need any other textbook,
what is the book?
No, it is written by him. Like it is himself. Like no other reference I have. Maybe I can come up with the reference in the next week. I'll let you know.
Okay.
Any question with respect to the idea how we approach this? Okay. Oh, okay. Once we calculate the value of NCO5, the next step is essentially to weigh this factor into our fitness function. So our objective is to essentially diversify our solutions. So we have to somehow tell our object algorithm to kind of penalize our functions which are kind of having less diverse. So when you have the original function as f, what I will essentially do is multiply it by some factor. I'm just calling it a factor as p that is dependent on this NCI in some particular format, which will kind of reinforce the value of f, and this will be my final objective function. So let me just not use pf, we'll use something else, say capital F. And this will be my final function that I will be trying to optimize. So now our optimization algorithm knows something about our diversity existing among the given solutions. So it will try to minimize this, but when it tries to minimize this particular value, it will also tries to minimize the value of NCI. When you are essentially trying to minimize the value of NCI, you will be minimizing the value of SA, which is kind of equivalent to saying increasing the value of Dij. So this is one approach about solving it. There is another approach which kind of, if you are implementing using genetic algorithm, say if you are using GA, we have a step where you do the crossover. There itself you can kind of implement this particular step. Like we have discussed previously, like crossover is essentially to kind of maintain the diversity within the solution. Like when you kind of get more and more fitness, when you apply the selection operator, what you are essentially doing is picking the solutions which are only feasible. I mean, which are only the best solutions. So that will kind of reduce the diversity. So crossover is done to increase the diversity. So there we kind of put only one criteria, which says if your crossover probability like is less than or equal to say some number of 0.8 or something, only then you do the crossover. But in addition to this constraint, we can put another constraint which kind of tells us not only the crossover rate, and then you also check the distance between the two parent individuals. If the distance between the two parent individuals, say I and j, similar we are denoting Dij, is less than or equal to sigma share, or let me put it the other way, is greater than or equal to some parameter, is greater than oh sorry. Let me just stick to this. Yeah, the idea is simple. So when we do the crossover, we have previously taken PC to be greater than or equal to 0.8. Now in addition to that, we will be adding one more constraint which essentially says the distance between the two parent individuals should be greater than sigma share. This should be our user parameter. This is kind of, the idea is simple. So when you have two parent individuals that are closer together, the offsprings will also be closer to the parent individual, so they will lead to less diversity. So when selecting parents, you need to select parents which are very far apart from each other so that the diversity will be maintained. This is another idea. So I think the time is up. We will take up examples in the next week. Yeah, thank you for joining.
Thank you.